Hello and welcome to yet another video of Cornerstones of Math. Today I've got this nice integral problem where we have this function f of x that is, well, quite unusual. Here function f of x is defined as the integral of the absolute value of 1 plus x times cosine t sine squared t dt from 0 to pi, which is an interval for t, by the way. Problem A. Show that f of x is an even function. That is, f of minus x is equal to f of x for all real numbers x. Problem B. Show that f of x is constant when the absolute value of x is less than or equal to 1. What is the value of f of x on this interval? Problem C. Find the value of f of square root of 2. Problem D. Can you express f of x without the integral on x greater than 1? What about on x less than -1? In problem E, can you find the asymptotes of the graph of y equals f of x when x goes to positive infinity and x goes to negative infinity? Also, in case you're interested in this problem, I prepared a similar bonus problem at the end of this video. That sounds cool and all, so let's get started. First, showing that f of x is an even function. Here we investigate f of minus x, which is an integral of the absolute value of 1 minus x cosine t sine squared t dt from 0 to pi. In order to find the relation between this function and the original function f of x, we use the substitution t equals pi minus u. This gives dt equals -1 times du. So we have integral, and the interval changes from pi to 0, absolute value of 1 minus x cosine pi minus u times sine squared pi minus u times -1 times du. Here cosine pi minus u is equal to minus cosine u, and sine squared pi minus u is equal to sine squared u. And with this -1, we can change the interval back to 0 to pi. Then we have the absolute value of 1, now plus x cosine u times sine squared u du, which is equal to f of x. Therefore, f of x is indeed an even function. Next, showing that f of x is constant on the interval absolute value of x less than or equal to 1. We need to investigate the sign of the expression inside the absolute value. Notice that when absolute value of x is less than or equal to 1, then x cosine t is less than or equal to absolute value of x and greater than or equal to minus absolute value of x. Therefore, 1 plus x cosine t is less than or equal to 1 plus absolute value of x and greater than or equal to 1 minus absolute value of x, which is greater than or equal to 0. That is, the graph of 1 plus x cosine t does not fall below 0 in our interval of integration. Therefore, we can write the integral as just 1 plus x cosine t sine squared t dt from 0 to pi. We can split this into integral of sine squared t plus x times integral of cosine t sine squared t. In order to carry out the first integral, we apply the trigonometric half-angle formula to change sine squared t into 1/2 times 1 minus cosine 2t. As for the second integral, let's use substitution sine t equals v. This gives cosine t dt equals dv. So this right here is dv. So it is x times the integral of v squared dv, but what would be the interval? Well, when t equals 0, sine t also equals 0, and when t equals pi, sine t equals 0. So the interval of integration is from 0 to 0, meaning that the value of the integral is 0. So the second term is 0. And since the first integral gives a constant value, we know that f of x is constant. Let's finish the first integral. We obtain the antiderivative 1/2 times t minus 1/2 times sine 2t. And if we calculate this, we obtain pi over 2. So fx has a constant value pi over 2 when absolute value of x is less than or equal to 1. Next, the value of f of square root of 2, and this is the part where things get a bit more complicated or a bit more interesting depending on how you see it. What's so big deal about this problem? Well, f of square root of 2 is the value of this integral. The integral of absolute value of 1 plus square root of 2 cosine t sine square t dt. And we have a problem with the absolute value part. That is, now 1 plus square root of 2 cosine t can have negative values in our interval of integration. And we have to flip the graph over t-axis when taking absolute values. So where does the graph become 0? Well, at t equals 3 pi over 4, where cosine t becomes negative 1 over square root of 2. Therefore, from 0 to 3 pi over 4, 1 plus square root of 2 cosine t is positive, so we just write 1 plus square root of 2 cosine t sine square t dt. And from 3 pi over 4 to pi, we have the negative part, hence we must reverse its sign. So we have minus 1 minus square root of 2 cosine t sine square t dt. So we split the integrals just like the previous problem, which gives us the integrals of sine square t and the integrals of cosine t sine square t. Here, the second and fourth integrals do not become 0, but we can apply the same method as in the previous problem. As for first and third integrals, we apply trigonometric half-angle formula and write 1/2 times 1 minus cosine 2t. And as for second and fourth ones, we use the same substitution sine t equals v, which gives this cosine t dt equals dv. So we have square root of 2 integral. Now the interval becomes from 0 to square root of 2 over 2, then v squared dv, and we have minus square root of 2 integral. Now from square root of 2 over 2 to 0, v squared dv. Therefore, we have antiderivatives 1/2 t minus 1/2 sine 2t, 0, 3 pi over 4. And notice that these two terms indicated here are the same, because by removing this minus sign, we can switch the upper and lower bounds of the integral. Therefore, we can combine these two terms and write plus 2 times square root of 2 times the antiderivative of v squared, which is v cubed over 3, with lower bound 0 and upper bound square root of 2 over 2. And then minus the third term, 1/2 t minus 1/2 sine 2t with 3 pi over 4 and pi. And if we calculate this, the first term gives 3 pi over 8 plus 1/4, the second term gives 1/3, and the third term gives pi over 8 minus 1/4. So we obtain pi over 4 plus 5 over 6. And now problem D, which can be considered the highlight of this video. Obtaining the expression for f of x without the integral on x greater than 1 and on x less than -1. So basically, we have to carry out the integral again. First, let's consider the case x greater than 1 for now. Of course, the problem here is that 1 plus x cosine t can become negative. Let us find out at which t does the graph cross the t-axis. This is the point where 1 plus x cosine t equals 0. So we obtain cosine t equals minus 1 over x. Hence t equals inverse cosine of minus 1 over x. Let's call this value alpha. Therefore, from the graph, the integral becomes from 0 to alpha, just 1 plus x cosine t sine square t dt. Then from alpha to pi, minus 1 minus x cosine t sine square t dt. So again, we split the integrals. Again, we replace sine square t with 1/2 times 1 minus cosine 2t. And we use substitution sine t equals v. Hence, cosine t dt equals dv. Notice that as for second and fourth integrals, the intervals of integration also change from 0 to sine alpha here, and from sine alpha to 0 here. Again, these two are the same if we switch the upper and lower bounds and switch the sign on the latter one. So we can write the antiderivatives as 1/2 times t minus 1/2 sine 2t for first and third ones, and 2x times v cubed over 3 for second and fourth ones. The first one gives alpha over 2 minus 1/4 sine 2 alpha, and the second one gives 2/3 times x times sine cubed alpha, and the third one gives minus pi over 2 minus alpha over 2 plus 1/4 sine 2 alpha. So if we simplify this, we have first 2/3 x sine cubed alpha, then minus 1/2 sine 2 alpha, then plus alpha, then minus pi over 2. Here, let's write this 1/2 sine 2 alpha as sine alpha cosine alpha. Now it's time to replace alpha with x, and here, we have to think carefully about where this alpha is located on the t-axis. In this case of x greater than 1, we know that alpha is greater than pi over 2 and less than pi. This means that cosine alpha is negative, but sine alpha is positive. That is, from here, cosine alpha is just minus 1 over x, which is negative by the way, and sine alpha must be positive, so it is positive square root of 1 minus cosine squared alpha, so root 1 minus 1 over x squared. So square root of x squared minus 1 divided by x squared, which can be also written as square root of x squared minus 1 divided by just x, because x is positive. Therefore, from here, f of x is equal to 2/3 x times x squared minus 1 to the power of 3 over 2 divided by x cubed minus sine alpha square root of x squared minus 1 over x times cosine alpha minus 1 over x plus alpha, which is inverse cosine of minus 1 over x, then minus pi over 2. We can write this as 2 times x squared minus 1 to the power of 3 over 2 divided by 3x squared, then plus square root of x squared minus 1 divided by x squared, and rest is the same. Inverse cosine of minus 1 over x minus pi over 2. This is the expression without integral, or rather the result of the integral, on x greater than 1. And the other case, x is less than -1, essentially follows the same step. If we draw the graph of 1 plus x cosine t when x is less than -1, we now have this graph. We do the same thing, finding the point where the value of the function becomes 0. The expression is the same as the previous case. We obtain t equals inverse cosine of -1 over x, which will be called alpha here as well. This time the graph is negative on the left region, hence we have integral from 0 to alpha -1 minus x cosine t sine squared t dt, and the graph is positive on the right, so from alpha to pi, integral of 1 plus x cosine t sine squared t dt. And now you know the drill. First, we split the integrals. Then we use the half-angle formula here. And substitution sine t equals v here. So we obtain these antiderivatives. And again, these two are combined. So from the first part, we have minus alpha over 2 plus 1/4 sine 2 alpha. And from the second part, we have 2/3 times x times sine cubed alpha. And from the third part, we obtain pi over 2 minus alpha over 2 plus 1/4 sine 2 alpha. And applying the sine double angle formula, we have, let's write minus 2/3 times x times sine cubed alpha first, and then sine alpha cosine alpha term, which is just plus sine alpha cosine alpha, then the alpha term minus alpha, then constant pi over 2. We need to convert this into a function of x, and this time alpha is greater than 0 and less than pi over 2, which means that cosine alpha is positive and sine alpha is also positive. Keep in mind that now we have the range x is less than -1. So from here, cosine alpha is -1 over x, which is positive by the way, and sine alpha is taking the positive square root, 1 minus cosine squared alpha, so square root of 1 minus 1 over x squared, so square root of x squared minus 1 over x squared. And we have to be careful here. If you want to write this as square root of x squared minus 1 on the numerator and writing x in the denominator, we have to add minus sign here because x now has negative values. If this confuses you, remember that the entire result must be positive since it is a positive square root of something. Therefore, we now have minus 2/3 times x times now minus x squared minus 1 to the power of 3 over 2 divided by x cubed plus now minus square root of x squared minus 1 divided by x times minus 1 over x minus inverse cosine of minus 1 over x plus pi over 2, which simplifies to 2 times x squared minus 1 to the power of 3 over 2 divided by 3x squared plus square root of x squared minus 1 divided by x squared minus inverse cosine of minus 1 over x plus pi over 2. This is the expression for x less than -1. Combining all the cases we've obtained so far, f of x is given as follows, divided into 3 regions, greater than 1, greater than or equal to -1, and less than or equal to 1, and less than -1. And let's move on to the final problem, finding the asymptotes of f of x at x approaches infinity and x approaches -infinity. Let's use crude method or approximation method first, only by considering the degrees of the functions. In x approaching positive infinity case, we have to use the expression of f of x for x greater than 1. As for the first term, this part x squared minus 1 to the power of 3 over 2 has a degree of 3. That is, it behaves approximately same as x cubed. So if we divide that by x squared, the entire first term is approximately x. As for the second term, the numerator is a square root of x squared, hence it is approximately x. So the entire second term is approximately 1 over x. And as for the inverse cosine term, since minus 1 over x approaches 0 as x approaches infinity, its inverse cosine approaches pi over 2. Here, notice that only the first term is approximately linear, and all the other terms either approach 0 or constant. That is, at x approaching the infinity limit, fx is approximately 2/3 times x, and the second term approaches 0, the third term approaches pi over 2, and the fourth term is minus pi over 2, which gives 2/3 times x. That is, f of x approaches the line y equals 2 over 3 times x. At x approaching negative infinity limit, we basically do the same thing with the expression for f of x at x less than -1. But we must be careful here. We must consider the sign of x so that first two terms stay positive. That is, the approximate function is now minus x, because now minus x is the one that's positive. And similarly, this part is approximately equal to minus 1 over x, which is positive, and the inverse cosine approaches pi over 2. So f of x is approximately minus 2 over 3x, and this term approaches 0, then minus pi over 2 plus pi over 2, hence minus 2 over 3x. That is, f of x approaches the line y equals minus 2 over 3x. Therefore, the asymptotes are y equals 2 over 3x when x goes to infinity, and y equals minus 2 over 3x when x goes to negative infinity. If you want to be more mathematically rigorous, you can show this using limits. First, when x approaches infinity, let us prove that the limit of f of x minus 2 over 3x as x approaches infinity is 0. That is, our original function minus the expected asymptote function approaches 0. If we use f of x for x greater than 1, we have this limit. Here, you can easily notice that the second term approaches 0 because it is degree 1 divided by degree 2. And the third term approaches pi over 2 since the inner part approaches 0. The only diverging terms are the first and last terms. So let's group them together to see whether the limit of this difference converges. So we write the limit of first and last terms, which is this, and the limits of the other terms are 0 plus pi over 2 minus pi over 2. Hence 0. Therefore, we only have the limit of, this can be written as 2 times x squared minus 1 to the power of 3 over 2 minus x cubed divided by 3x squared. We have infinity minus infinity limit on the numerator. So let's see if multiplying x squared minus 1 to the power of 3 over 2 plus x cubed on both numerator and denominator eliminates such form. So now we have 2 times square minus square, which gives x squared minus 1 cubed minus x to the 6th power and the same denominator. And you can easily expand the numerator. And if you do that, you realize that the 6th power term is eliminated. The only thing left here is minus 3x to the 4th power plus 3x squared minus 1. The entire limit is in infinity over infinity form, which can be evaluated by comparing the degrees. The numerator has degree 4, and the denominator has degree x squared here, and x cubed here, hence x to the 5th power. Since the denominator has higher degree, the limit is 0. So we have proved the first limit. And as for x approaching negative infinity case, we now want to prove that the limit of the difference between fx and minus 2 over 3x approaches 0 when x goes to negative infinity. So now we use the expression of f of x on x less than negative 1. Again, the second and third term converges, so we only group first and last terms and split the limit into first and last terms and the other terms, which is 0 by the way. So now we have 2 times x squared minus 1 to the power of 3 over 2 plus x cubed divided by 3x squared. Note that the numerator is still in infinity minus infinity form because now x is negative, hence this x cubed is also negative. In order to eliminate this form, we multiply x squared minus 1 to the power of 3 over 2 minus x cubed on both numerator and denominator. So we have this, and by simplifying the numerator, we obtain this. And here's the important thing. Since x is negative, this part of the denominator is actually in infinity plus infinity form. Therefore, we can just compare the degrees, and again, the denominator has larger degree, hence the limit is 0. So we have proved the second limit, which gives us the same conclusion about asymptotes. Now, if you want some graphical visualization, this is the graphical visualization of function f of x. As you can see, the graph is constant between negative 1 and 1. And you can also clearly see that f of x approaches two different asymptotes, y equals 2 over 3x and y equals negative 2 over 3x. Lastly, the bonus problem. If you understood what I have explained so far, then you may be able to easily solve this bonus problem as well. So if you want to do some more math for fun, here's the bonus problem for you. This time x is located here, so that the inner part of the absolute value is x plus cosine t. Also, if you want more videos similar to this one, then you may also check out this video listed at the top, which features the function of a similar type. Thank you for watching. Please don't forget to press that like button, and I will see you in another video.